Hi, I'll go over lab one of ECE 286, which is steady state RC and RL series circuit. So this lab has a lot of repeating experiments. So lab one and lab three are pretty similar, and lab two and lab four are essentially the same thing. So lab one and lab two, sorry, not lab one and lab two, experiment one and experiment two use a RC circuit, while our experiments three and four use a RL circuit, but the procedures that you use for experiments one and two will be the same for three and four respectively. So I will only show how to do experiments one and two, but like the same procedures you used for experiment one and two will be used for experiments three and four. Okay. So experiment one, you have a series circuit where you're varying the frequency and you're measuring the response of the components. You're using a 100 nanofarad capacitor with a 1K resistor, and you're measuring the voltage drop across the resistor and capacitor and the relative phase shift of the power supply compared to the resistor and capacitor. So what I'll first do is I'll show you my setup. So here's my circuit. This is my 100 nanofarad capacitor right here. This is my 3K resistor. I swapped the 1K for a 3K. And here's my ground cable right here. This green cable is connected to my yellow cable from my M2K, which is my wave gen cable. This is my solid orange cable that's connected to the power supply node. This is the negative to channel one, which is connected to that node where the resistor and capacitor share. And channel one will be measuring the voltage drop across this capacitor. And then I have my positive of channel two connected at the node where the resistor and capacitor meet, and then the negative of channel two connected to the ground. And there's a black cable coming from the M2K to ground my whole circuit. Okay. So now I'll switch over to my M2K. I'll go ahead and click connect when you open up Scopy and give it a moment to connect. Okay, perfect. So now you want to supply a signal with a 4-volt peak to peak or a 2-volt amplitude at 3 different frequencies, which is 500, 1K, and 5K. I'm going to show the 500 hertz, and then I'll keep my offset phase as 0 because I don't need to worry about that. And then I'll go ahead and click run at the top right of the screen. I'll switch over to my oscilloscope. And the objective is to measure the phase shifts along with the actual voltages. So if I want to measure phase shifts relative to the power supply, I need 3 signals. And the way to do that with the way I have my circuit set up is measuring the voltage drop across the capacitor, which is channel 1, and adding it to the voltage drop of the resistor, which is channel 2. So channel 1 plus channel 2 would lead to the input voltage. So I will do that by clicking this plus right here. And then I'll click on this dark blue button, and then it has a drop down which shows T0 and T1. T0 corresponds to channel 1. T1 corresponds to channel 2. So I'll do T1 plus, where did the plus go? There it is. Plus T1, which indicates channel 2. Go ahead and click apply and then click add channel. So right now it's going to show up as a solid line because it has no data to show. So I'm going to go ahead and click single. And then here we go. So if you're looking at this waveform, you would see how the supply voltage, which is our math function, does not necessarily add up or make sense with our waveforms. And that makes sense because of the scale of each waveform. So channel 1 and channel 2 are on the same scale, but channel 3, the math function is on a 1 volt per division scale. So you need to change that. So what I'll just do is change everything to 500 millivolts. And the way you do that is to the right of channel 1, channel 2, and the M1, there's this interesting looking button with 2 parallel lines, and then that gives you channel 1 setting. So if you want to if you want to shorten it, if you want to shorten the horizontal axis, you can. If you want to make the graphs super small, you can. If you want to blow up the graphs, you can decrease that division rate. And then I'm just going to do this for all of these. So I just want to get a good accurate representation of my waveforms. So there we go. And then now you want to measure the actual peak to peak voltage or just the amplitude. The way you do that, if you go over here, there is solid buttons to the left of certain items. So the cursor has a left button and a right button along with measure and on the channel. So if you want to disable a specific channel, let's say you don't green channel because it looks ugly. So you can click on the green button and then that will disappear, but it will still be there. You can always like turn it back on by re-enabling it. But if you want to measure the voltage drop, you want to click on the measure, click on the button. And then now if you look at the top, you'll see the period, the frequency, the peak to peak, and the mean. You don't have to necessarily worry about the mean. But if you look at the peak to peak, that's what you care about because you can relate peak to amplitude, which is half of the peak to peak is your amplitude. And so you see how the green, which is supposed to be our input source, is almost 2 volts as an amplitude. And that's pretty close. So yeah, so this shows the amplitudes, and now you want to measure the phase shift. So what you're going to do is you're going to enable your cursor by clicking that little button to the left of the text cursor. And then you're going to click on the button to the right with the 2 parallel lines, and then enable or toggle the switch from normal to track. So now you'll have 2 gray vertical bars. So what I'm going to do is I'm going to place my first one around the peak of my input voltage, which is my green, and then I'll measure it across the peak of my orange waveform. Let's see. So it's roughly there. And then now I'm going to come up here where it says delta T. It's about 260 microseconds, and you can use that change in time to relate to your phase shift. So the change of time times 2 pi divided by the period will give you the approximate phase shift. So since you're using cursors, it might not be exactly precise, but there is, you will get pretty close. And then you would repeat this for the purple waveform, which is my resistor's phase shift. The orange is my capacitor's phase shift. Okay. And then that essentially goes over how to do experiment 1. And then now I'll switch over to experiment 2. And so you still have that same RC circuit, but you're varying the resistance, and you want to measure or identify the frequency where both the voltage drops across the resistor and not inductor for the capacitor equals one another. So you could always measure the frequencies manually and see at what frequency they do equal each other, which is a pain, but it is possible. But there's a beautiful feature of this device, which is called a network analyzer, which will do a frequency sweep. And that's essentially what we're doing if you were going to switch between frequencies. So what I'm going to do is I'm going to go to the settings of my frequency sweep, which is not the gear, but the 3 parallel lines. So this is a particular way there's a particular way to measure the frequency sweep. So you need a reference. So one of your, let's say one of your channels has to measure the voltage drop being supplied. So for this case, you see how my yellow cable, which is turning into my green. So let's just say the green and the black, that's my input voltage, right? Either my orange has to go across the green and the black, or my blue has to go across the green and the black. That's the only way to do it. Otherwise, you won't get proper results. So what I'm going to do is I'm going to switch my channel 1 and measure it across the supply voltage. So channel 1 and the input voltage are being, channel 1 is measuring the input voltage. And then I'm going to switch channel 2 and measure the voltage drop across the capacitor. There we go. Is that in? Yeah, that looks good. So now channel 1 is my input voltage. So I'm going to switch it to 2 volts because that's what states in the lab manual, I believe. Yes, it does. And I'm still using my 3K resistor, but you can swap out the 1K with 100 or 10K, however you do it, but make sure you keep track of everything. And then I'll go ahead and click run. But before I do, I'll scroll all the way down. You could always increase the number of samples. So if you do like 2,500 samples, per decade, you'll have a long time, or you have to wait a long time, but I'll keep it at around 50 just so this recording goes pretty quick. So I'm measuring the voltage drop across, or the frequency for the capacitor specifically. And as you look at the magnitude plot, you don't necessarily have to worry about the phase. The magnitude behaves, or the frequency response of that capacitor makes sense. At low frequencies, you have a higher voltage drop compared to at higher frequencies. And that's what you're seeing in this dB scale. Okay, so we want to measure the resistor's voltage drop as well. So the only way to do that is if you click the gear at the top right and then click snapshot, this will remember this waveform specifically, just this one. And then now I will switch over to this and swap my channel 2 cables and put it across my resistor. So now it's across my resistor, and then I'll go ahead and click single, and now you'll have two overlapping waveforms. Again, you don't have to necessarily worry about the phase because the phase doesn't matter for us right now, but the magnitude definitely matters because we want to measure at what frequencies both the voltage drops across the elements equal one another. And that intersection point right there is that frequency that we care about. So I'll give it a moment for this to complete its frequency sweep. Let's see. Okay, cool. And then now at the bottom right, I'm just going to go and enable the cursor. That's a lot. Go to the settings. Okay, I can't change that. So it's okay. So now I'm going to switch the positions to the right because the frequency we care about is on the left. And then I'm going to approximate it around there. And so now if you look at the frequency of F1, which is not, which is the one that we care about, you'll see it's 514 hertz. And that's a frequency when a 100 nanofarad capacitor in series with a resistor of 3K has the same voltage. So now you can easily do the experiment 3, which is following these procedures of experiment 1, and then experiment 4, which is following the procedures of experiment 2, which I just did.